In this video, we're going to find all of the x-intercepts of a polynomial equation by factoring. So before we can find x-intercepts, we need to review what an x-intercept actually is. So remember that an x-intercept is a key location on a graph. And if we were to have some sort of graph that looks like this, the x-intercepts occur whenever we cross the x-axis. So if you look at this particular polynomial function here, we have 1, 2, 3 x-intercepts. So the first thing we need to know is that these points occur when we cross the x-axis. The other thing we need to know about these points is all of these points occur when the y value is equal to 0. So their coordinate point is some x value, comma, 0. So that's what we know about the x-intercept point. It occurs on the x-axis, and whatever point it is, it always has a y value that is equal to 0. So in this example here, we're going to utilize factoring to find the x-intercepts of the polynomial equation. Now remember that the x-intercept points we know occur when y is equal to 0. So what we're going to need to do here is set y equal to 0. Now it looks like there's not a y value in this particular equation, but we need to remember that that term f of x is really a fancy way of saying y. So what we can do here is we can turn our entire f of x term into 0, and that will change our y value into 0. So in doing so, we're saying we want to find all of the x values when y is equal to 0. Now, from looking at this, the only way to really solve a polynomial equation based on what we know right now is to utilize our factoring strategy. So what we're going to do is we're going to factor this entire right side of the equation, and then we're going to use what's called the zero product property to solve this equation. So if we look first, we know that the first factoring strategy that we always use is the greatest common factor strategy. Now if I look here, 4x cubed, 2x squared, and negative 12x are all divisible by a 2, and then they all contain at least one x. So in factoring out the greatest common factor of 2x, I'm left with 2x squared minus 1x minus 6. So I've utilized my first strategy of the greatest common factor, and now I need to look at the trinomial that's left and decide what other strategies might be applicable here. Now I can see from looking at this particular polynomial that this is not a difference of squares, difference of cubes, or sum of cubes because it doesn't have those special values. I can also see that this isn't a factoring by grouping problem because there aren't 4 terms. So I'm deducing that this is a great candidate for the ABC method. So we find we have A is equal to 2, B is equal to -1, and C is equal to -6. I then know that I need to find two numbers that multiply to be what A times C is. So 2 times -6 is -12, and these two numbers need to add to B, which is -1. So I need two numbers that multiply to -12, but add to -1, and I come up with -4 and 3. So from here, I can rewrite this to be 2x squared minus 4x plus 3x minus 6. So I use my two values here to rewrite my trinomial. Then from here, I use factoring by grouping. Find the greatest common factor in each group. So this first group is 2x. So if I factor out a 2x, I end up with x minus 2. And then if I factor out a 3 here, I again end up with x minus 2. So because my two parenthesis pieces match, I can group their coefficients together. So I ultimately end up with 2x plus 3 times x minus 2, and then bring down this 2x, and that's all equal to 0. So right here is my fully factored polynomial form. Now, if we were just being asked to factor, this is where we would stop this problem. But because we actually want to solve this and find those x-intercept values, we need to use the zero product property. And what I notice here is that I have 1, 2, 3 items being multiplied that equal 0. And remember, the zero product property states that if we have items being multiplied, which in this case we have 3 items being multiplied, and they equal 0, that if one of them equals 0, the whole thing equals 0. So we have 3 possible x values here for our x-intercept. One occurs when that 2x is equal to 0. One occurs when 2x plus 3 is equal to 0. And one occurs when x minus 2 is equal to 0. If any of those 3 components equals 0, then the whole thing will be true. So we solve each one. This first one we divide by 2. We find x is equal to 0 is one option. Here we subtract 3. And then we divide by 2. So we find x is equal to a negative 3 over 2. And then here we add 2. So we find that x is equal to 2. So here we have 3 possible values for x. We have x equals 0, x equals negative 3 halves, and x is equal to 2. So our last step here is to actually list these as x-intercept points. So our x-intercept points occur when x is 0 and y is 0. Then when x is at negative 3 halves and y is at 0. And when x is at 2 and y is at 0. So here we have our 3 x-intercept points. And these are the 3 points where we would cross the x-axis for this particular polynomial. So let's repeat this same process here in example 2. So again, we're going to utilize factoring to find the x-intercepts of the polynomial. And again, we note that in order to do this, we need to find what the x values are when our y value is equal to 0. So we're going to start by taking f of x, which is really a fancy way of saying y, and replacing it with 0. So we're trying to find the x coordinates that make this particular equation true. Now, to start, I'm going to use the greatest common factor strategy. And here, because I don't like having an a value that is negative, I'm actually going to factor out a negative 2 because all of these terms are divisible by 2. And if I divide by a negative 2, I can remove that negative a value there. So here, if we factor out negative 2, we end up with x to the 4th minus 8 squared plus 16. So that's our first step there. Then I look here, and I notice that I have a trinomial left. Now this might look like it's not really factorable, but because x to the 4th is twice as large as x squared, and then there's no variable here on the 16, this can actually be factored just like our ABC trinomials. So what we're going to do here is we're going to start by finding our a, b, and c values, just like we normally would. So a is 1, b is negative 8, and c is 16. Now, we need two numbers that multiply to be a times c, which is 16, and add to be b, which is negative 8. And when I think about it, the two magic numbers that multiply to be 16 and add to be negative 8 are negative 4 and negative 4. They multiply to be 16 and add to be negative 8. So we can now rewrite this trinomial to be x to the 4th minus 4x squared minus 4x squared plus 16. So notice that I just wrote that negative 8x squared to be negative 4x squared minus 4x squared. Now we're going to group these into pairs and find the greatest common factor. So in this first one, the greatest common factor is x squared. So that becomes x squared minus 4. Then in the next set of parentheses, I factor out a negative 4. And in doing so, I also get x squared minus 4 inside those parentheses. And then from here I can group them, and I can say, well, I have x squared minus 4 out here, both being multiplied by x squared minus 4. Then here I can bring this negative 2 down and set that all equal to 0. Now, it might appear that we're done, but if we look really closely here, this one actually has a few tricky parts. If we look at what's left, both of these contain an x squared. So that means that we might be able to factor it further. And if I look closely here, I notice that both of these happen to be a difference of squares. This is x squared minus 2 squared. And this one is x squared minus 2 squared. So I can actually factor both of these further. This one becomes x minus 2 x plus 2. And this next one here also becomes x minus 2 x plus 2. And then I still can bring this negative 2 down and set it equal to 0. So this one has quite a few little tricky parts to it. It factors using the ABC method up here. And then because we have those x squares, we can use the difference of squares down here. So now that this is fully factored, remember I can use that 0 product property to set all of these components equal to 0. So what I'm going to do here is I'm going to take all 5 of these components. So you can see we have 1, 2, 3, 4, 5 items being multiplied and they equal 0. So if any of them equal 0, the whole thing is true. So I'm going to start here and find when negative 2 equals 0. Then move on to this next one. So I have x minus 2 equals 0. Here I have x plus 2 is equal to 0. Here x minus 2 is equal to 0. And here x plus 2 is equal to 0. So then if I go through and I solve all of those, well, negative 2 can't ever equal 0. There's no variable there. So that one doesn't help me at all. This next one here, I'm going to add 2 to each side. So I find x is equal to 2. Here I subtract 2. So I have x is equal to negative 2. Here I add 2 again. So I have x is equal to a positive 2. And here I subtract 2. So I have x is equal to a negative 2. Now what you're probably noticing is that we have some duplicates in here. This fact is actually really important for what we're going to cover in the future. So note that here we have 2 situations where x is 2. So here I'm going to record my x-intercepts, but I'm going to record if there are multiples. So here one of our x-intercepts is when x is 2, y is 0. And I'm just going to make a note here that there are 2 of these. And then I also note that there's x equals negative 2 and x equals negative 2. So I have another x-intercept at negative 2 comma 0. And I'm again going to note that there are 2 of them. So we're going to cover in the future what this actually means, why we have to note that there are 2. But for right now, all you need to know is how to factor a polynomial to find its x-intercept points, and then note if there happen to be more than one that repeats of the same value.